Hi, welcome back to this video series on cryptography. In this segment, we will analyze the affine cipher. The encryption proceed as follows, right? If you have an input X, X could be a number between say 0 through 25 inclusive. If you are encoding or encrypting more precisely English alphabet letters, right? Um, how will we encrypt X? X will be encrypted using A times X plus B. A and B are private keys, right? Only the sender or the person who's encrypting the message X will know that. And we do modular arithmetic. Usually, if you are talking about English alphabet, it is just 26, right? The 26 possible alphabet characters, alphabet letters. It need not be just 26. It can be any M per se. You can replace this by any modulus you like. Okay. X is a number, right? In English, it will be from 0 through 25 inclusive. 0 stands for A, 1 stands for B, and so on. So this is how we encode. And let me call this encryption output as Y, right? We get a Y here. We send Y to the decryptor, who is going to decrypt Y as follows, right? First thing she has to do is get rid of B, right? And that means she's left with A times X. So in order to recover X, she has to get rid of A. Multiplication is there during encryption. That means you need to do opposite, inverse, right? A inverse mod M. And A inverse exists only if A is relatively prime to modular arithmetic value. For example, A must be relatively prime to 26. Otherwise, decryption is impossible. Okay. We talked about this in the previous segment. Okay. Now the question is, suppose you are seeing two pairs of ciphertext, plain text. Okay. Suppose you are seeing, say, let's assume you know X1 gets mapped to Y1, meaning encryption of X1 will give you Y1, encryption of X2 will give you Y2. Okay. So this is called known plain text type attack, right? You know two pairs of plain text ciphertext. Can you now find the values for A and B? Those are remember the private variables. Okay. How do we do that? It's easy to do that as follows. So since you know X1 gets mapped to Y1, now I can use the equation number 1 as follows, right? I will just compute or rewrite equation 1 as follows by substituting X1 there. So I have A X1 plus B, right, is congruent to Y1 mod 26. Okay. There's nothing specific about 26. You can replace it by any other modular number you like. Okay. It has to be the size of your alphabet set. Okay, that's all. And A times X2 plus B is equal to Y2, incongruent Y2. Okay. Now it's easy to break this. All we have to do is apply basic linear equations. How to solve two linear equations with two unknown variables. The unknown variables are A and B, right? X1 and Y1, X2, Y2 are known. We know it. So if we now solve this equation number 3 and 4, we are done. We can easily solve that because we have two equations with two unknown variables. So if I just subtract 3 from 4 or 4 from 3, doesn't matter. Let me do 3 minus 4. I'm going to get A times X1 minus X2, right, is congruent to Y1 minus Y2. I'm just applying the rules of modular arithmetic here, right? Times, this is done in mod 26, okay, or mod M more generally, okay. So we know X1 minus X2, we know Y1 minus Y2. So how do we get rid of those things and find A? We can easily find it because all we have to do is compute X1 minus X2 inverse, okay. I'm going to make an assumption here that the inverse of X1 minus X2 exists, which may not always be true. If M is prime, then we know for sure it exists. But in this case, you're dealing with 26, which is not a prime. So X1 minus X2 may not have the inverse. But let us assume that you did have you did find an inverse. Okay, in that case, A is nothing but x1 minus x2 inverse, right, times y1 minus y2. Okay, so you found A now. Once you found A, you can go back to equation number 3 and find B easily, right? Because you just have only one variable left. Okay, this is also in mod 26. That's all. This is how you break affine cipher. As a matter of fact, there's an interesting lesson here. You don't want to have your cryptographic construction based on just linear combination. Okay, here's a linear combination. We combine some amount of secret with the plain text, right? This is strictly speaking affine transformation because we are adding a constant. Affine is also not good. Okay, you don't want to do this combination of key with your message. No, that's not a good pattern. Okay, now let me give you a concrete example to get this idea across. Let us assume that in the previous segment we talked about encrypting a piece of plain text. I think it's called HOT, but I'm going to just take only HO. Okay, HO is one plain text. It gets mapped into another ciphertext, right, by the encryption process. Okay, so let's say this is the plain text. Okay, and we don't need to know about T. Okay, let's say only you know two characters, H and O. Let's assume H gets mapped into A as a ciphertext, and O gets mapped into X. Okay, the question now is, can we find A and B? Okay, those are the secret variables, right? Remember, this is plain text. This is plain text. I call it P for a moment, and this is the ciphertext. Okay, so how are we going to solve that? Well, all we have to do is we have to just use the encoding. H gets mapped into an English character to number system. If you start A to be 0, B to be 1, and so on, H will be 7. So my equations are as follows. Let me clear this whole system and rewrite it. Okay, so my equations will be A times 7, right? Because I'm talking about plain text being HO, right? H is my first character, O is the second character, and my ciphertext is AX. Okay, meaning we apply affine transformation on this input and we got this output. Okay, now the question is, can we learn A and B? We can, as follows. H is nothing but 7. If you encode each alphabet letter of starting from 0 all the way through 25, mapping A to Z. So we have the first equation, A times X is H, right? H is nothing but 7, plus B, we don't know B, is nothing but what is the first thing? First equation is, we are mapping it to A is 0. Okay, so it's 0 in mod 26. What is the second equation? We are taking O is 14. So you have A times 14 plus B is nothing but X. What is X? We just subtract, say for example, the second and the first. What we will left with is 7 times A is congruent to 23 in mod 26. We are doing all of this in mod 26, by the way. Okay, so we do know 7 is relatively prime to 26, so 7 inverse must exist. Inverse in mod 26 is nothing but 15, because 7 times 15 is 105, which is nothing but 1 in mod 26. So this turned out to be, if you solve this equation, this turned out to be A as 7. Okay. Okay, so A is, let me rewrite this. A is 23 times 15. Where is 15 coming from? 15 is the 7 inverse in, let me write it here on the side note. 7 inverse is equal to 15, because 7 times 15 is 1 in mod 26. Okay, so this is basically what I have in mod 26, which gets simplified into, again, surprisingly, 7. So A is actually 7. All right, so that's basically the first part. Okay, first part of the equation we solved. Next part is easy. All we have to do is we can go back and plug a equal to 7 in one of these equations. Let me call this equation number 1 and equation number 2. So if we plug it in any of these equations, we can easily plug in. So 7 into 7, 49. 49 is congruent to, so we have this equation 49 plus b is congruent to 0, okay, mod 26. All you have to do is just solve that equation. My minus 23 is nothing but 3. Okay. All right. So we found the a and b. That's it. These are the secret values. And you are able to find a and b. Okay. That's all. Thank you very much for your attention.